Hey guys, welcome back to another lesson. Today we are going to learn about the derivatives of the other trig functions. So tan, secant, cosecant, and cotangent. So today's lesson will kind of, the way it will work best is if you maybe want to, as I set up a problem, if you want to pause the video and try it yourself. And wrestle through that. And then you can unpause if you need a hint or if you just want to kind of check your final answer and compare how we did things. So let's get started. So first, we just have to make sure we remember our other trig identities that you guys learned in grade 11. So the first that you guys learned in grade 11, along with the Pythagorean identity, which is, and we talked about this one in one of our previous video lessons, but the one identity that everybody should have, like almost automatic, is this Pythagorean identity. Sine squared theta plus cos squared theta equals 1. So that's an identity that's true for whatever angle you plug in there. The sine of an angle squared plus the cos of an angle squared is always going to give you 1. You guys learned that in your grade 11 course. But a second one you guys learned was this one. It was that the tan of an angle is equal to the sine of an angle divided by its cosine. And this was called the quotient identity. And then you guys learned your reciprocal identities. So the reciprocal of sine was cosecant. The reciprocal of cosine was secant. The reciprocal of tan was cotangent. And today we're going to find the derivative of these trig functions. So you will notice they are all quotients. So we'd be able to use the quotient rule to find the derivative of all these guys. You could also, for the middle two, write those as a power, like sine theta to the power of -1, cosine theta to the power of -1. So in this investigation, I may mix up strategies just to mix it up. But there are multiple ways to find these derivatives. So let's get started. So we're going to start with tan x, and we're going to show that the derivative of tan of x is secant squared x. This is almost one of a basic derivative that we want to, just like we know that derivative of sine is cosine and cosine is minus sine. This is another one that is useful just to have in your math toolbox. It occurs often enough that you just want to have it almost be automatic. But let's show that that's true. And we do it by writing tan as sine x over cos x. Because we already know those two derivatives, and we know how to find derivatives of quotients. So we should be able to do this. So I'm going to do this one with you. Although if you are feeling adventurous, feel free to pause the video and just do it on your own. So y prime. So using the quotient rule, we take the derivative of the top, which is cosine. Write the bottom up top, cosine x, minus, we write the top down, sine x, and we take the derivative of the bottom. The derivative of the bottom is negative sine. All over the bottom squared. So cosine squared x. Some of you may see where this is going already. If we clean the top up, that's cosine squared x. Negative, negative, that's plus sine squared x, all divided by cosine squared x. And just a few minutes ago in this video, we talked about one of the identities that everybody should have in their math toolbox, and that's the Pythagorean identity. Sine squared plus cos squared is equal to 1, or cosine squared plus sine squared, that is equal to 1. And so this is just equal to 1 over cosine squared x. And if you recall, the very definition of secant x is 1 over cosine x. This is actually just equal to secant squared x. And we've shown the derivative of tangent is secant squared. So that's pretty cool. And this is just something that you can use. Now just pull it all the time. You don't need to write tan as sine over cosine and do the quotient rule. You guys now know the derivative of tan x is secant squared x, and you can just use it all the time. So now that I've kind of given you guys an idea how you could do this, you could try this derivative on your own. I'm going to try this one by writing cosecant x as a power. I'm going to write that, so it's 1 over sine theta, or 1 over sine x, excuse me. But I'm going to write that as sine x to the power of -1, just to mix things up. And let's find the derivative. So dy by dx, I'll use Leibniz notation here. So this is a power of function. So we'll bring down the exponent, and then leave the inside alone. So negative sine x, take 1 off the exponent, that's -2. And multiply by the derivative of the inside, which is cosine x. That is it. Let's clean it up though. So I can write that as negative cosine x over sine squared x. Now that is the derivative. Obviously, the up here, negative cotan x, cosecant x looks a lot different, but we can actually show that these two things are equivalent. And we can do it this way. I can write this as a product of two rational expressions. I can write that as negative cosine x over sine x times 1 over sine x. And by doing that, you can see that these two are actually equivalent because, well, we've got that negative sign. Cosine over sine, that is equivalent to cotan x. And 1 over sine, that is equivalent to cosecant x. And we have shown that the derivative of 1 over sine, or cosecant, is negative cotan x times cosecant x. And we did that one by writing the function as a power to the power of -1. You could have also done that the same way using the quotient rule. You would have got the same answer. So let's go on to part C, and I'll leave this with you guys. So I've shared two strategies with you. Why don't you try this one? Show the derivative of secant x is tan x times secant x by either writing it as a quotient or writing it as a power to the power of -1. If you'd like to pause the video, give it a try. You can unpause when you're ready, or you can follow along with me right now. Let's give this one a go. So I'm going to do this one using the quotient rule just for fun. So I'll write that as 1 over cosine x. And how does this look like with the quotient rule? Well, quotient rule says take the derivative of the top, which would be 0, and write the bottom up top, minus, write the top down, which is 1. And the derivative of the bottom is negative sine x all over cosine squared x. And we get sine x over cosine squared x. And that is correct. That is the derivative purely in terms of sines and cosines. But we can use a similar trick that we've done in the past to write that as tan x times secant x. I'm going to break this up as sine x over cosine x times 1 over cosine x. And now you can see sine over cosine, that is equivalent to tan x. 1 over cosine is equivalent to secant x. And we did it. We showed the derivative of secant x is tan x times secant x. Not so bad. On to the last one. The derivative of cotan x is negative cosecant squared x. And we're going to show it. So as usual, pause and try it on your own. Unpause when you're ready, or follow along with me right now. In this one, we'll write cotan x as cosine x over sine x. And so this one is set up for us to use the quotient rule. Take the derivative of the top, negative sine x. Write the bottom up top, sine x. Minus, write the top down, cosine x. Through the bottom is cosine x. Over the bottom squared, sine squared x. So what we have here, you'll notice we have a negative and a negative. So in cleaning this up, I'm actually just going to write this like I'm going to factor out -1. So I've got my negative and then sine x times sine x, that's sine squared x. I factored out that -1. So from my second bit, I have cosine times cosine, cos squared x, all over sine squared x. And then sine squared plus cos squared, we love seeing that because we know that simplifies to 1. And we get -1 all over sine squared x, which is the very definition of negative cosecant squared x. And we did that one too. Guys, those are our the derivatives of the other 4 trig functions. Some occur in applications more than others. I mentioned before that the derivative of tanx is a useful one to have just in your toolbox. It does show up often enough in a variety of applications that it just makes life easier to have it down. Admittedly, cosecant x, secant x, and cotan x don't show up a lot in various applications. To be honest, if you ever needed those derivatives, you could honestly just like look them up. You could rederive them every time or have them memorized, but a lot of you guys will just eventually just like the one time in 100 you might need that. It's just, look it up in some resource in a textbook on the internet. So that's it for today, guys. For suggested practice, there are a few questions from the previous section. Section 4.3 in the McGraw-Hill-Ryerson text that have some questions. Some of them are repetitive, like we just derived the derivatives of those 4 trig functions, so you don't have to redo those. But 18 and 19 are just some fresh questions you can try. And on the PDF lesson sheet that I've posted on our Google Classroom, there's some extra practice on the back that mainly focuses on tangent. And so if you guys just have, keep the lesson we did out and just want to rewrite that as the derivative of tanx is secant squared x. You're going to use that a lot in that practice. It focuses mainly on tanx. And so you're going to be using the product rule, the quotient rule, the chain rule, all with tanx. You'll be finding equations of tangent lines with functions involving tanx. You'll just be doing all of our usual calculus stuff just with the tangent function. So you have that practice to do as well. I feel like I've posted enough content to keep you guys busy for a little bit. It is hard to know the pacing and how you guys are feeling since we're doing this remotely and I'm just like shooting videos. So my plan is for Monday to not post a new lesson, but on Monday, I'm going to make myself available I'm available all day, but I'm going to make myself available from 9 a.m. to noon just to field questions from you guys. So I'll just be at my computer doing work. And you can shoot me questions via email if you want. But, we all use the Google Suite for our Halton School Board like school accounts. We all have access to the Google Hangouts app, which is just basically like video conferencing where, we can chat like this. I can actually share my screen with you. So I can share a virtual whiteboard and like write on the whiteboard. And if you want a bit of extra help, that's Google Hangouts would be great. So, it'd be great to try that with a few of you guys on Monday. It's just nice to have a little face-to-face action too. I know myself, I've really enjoyed actually kind of getting back to work the last few days. I'm not sure about you, but I've really enjoyed having something meaningful and productive to do, work-wise at least. The second thing I wanted to add is that like if you finish this stuff, if you want something else to work on, I can get extra practice for you. That's not hard. So if you want more to do, if you'd like a suggestion on something you could learn that's a bit above and beyond the scope of the course, just ask and I'll definitely provide it to you because I know a lot of you guys are working hard. You might be getting ahead. And if you want something to do, I can give you something meaningful to do. Not just busy work, more practice if you feel like you need more practice. But yeah, if you want to learn something interesting, I might not shoot a video lesson about it, but I can point you to like a Khan Academy and get some practice on that subject for you. So please ask. All right. And on Tuesday, I'll probably post a new video lesson. The next thing we'll cover is applications of trig functions, and maybe doing some optimization problems with trig functions too. All right, everybody. So stay busy, stay healthy. We'll see you guys soon.